Okay, now we study section 3.5, is about graphic technique and transformation. Okay, in conclusion, when you adding plus one constant, the vertical shift and go up. When you subtracting any constant outside, it's down. Okay, suppose another transformation in which you multiply a function by a constant. Again, we start at one point on the original graph. I want to investigate what happened when you transform this point using this new idea. Okay, so now y1 is equal f evaluating x1, and y2 is k multiplication f evaluating x2. If you suppose x1 and x2 are the same, then y2 is equal k times y1. And this is the relationship. The relationship is the same x, you suppose, comma, and k multiplied by the second component y is multiplied by k. What is the interpretation of this graphically? The interpretation is, suppose a graph of the original function, and suppose one arbitrary point, x1, y1. When you apply the transformation and you multiply by a constant, the second component is increasing if k is bigger than 1. So k is bigger than 1, like a 2, like a 3, like a 4, like a 3.5. Okay, now the second component y is increasing by the factor k, and the graph looks like that. And this is called vertical stretch. Okay, when the k is greater than 1. When the k is less than 1, so in between 0 and 1, so now fraction, the y transform is decreasing, and the effect is vertical compress. However, one special case interesting when the k is -1. When the k is -1, this is the original function but a completely opposite sign. Is reflection about x-axis. Okay, let's see much better the effect when you multiply by a constant outside the function. And this is vertical stretch, compress, or reflection. In this case, I suppose guess 1. 1 is the original function. Okay, I suppose one example is a square function. However, you multiply by a number, look at what happened. Multiplication, wow. It's typical vertical stretch. Look, let me see 4. 4 is here. Not necessary. What happened with the value? The value is, for example, the value of the x stays the same, but the value of the y is multiplied by this number, right? So the value of the y is affected by the factor. In this case, suppose 2. 2.1, 2.2, 2.2. Entonces 8.8, because the original was 4, no? 4 multiplied by 2.2 is 8.8. Likewise happen when you multiply by the number less than 1, like a 0.6. This is compressing. Do you see it's compressing? Compressing, vertical compressing. When you multiply by a constant less than 1. Okay, ahora what happens when it's negative? Well, when it's negative, it's supposed specifically negative 1. Well, negative 1 es no positive, sí, pero es obvio que es reflection about the x-axis. Let's see the animation. This is stretch, vertical stretch, when the coefficient is greater than 1. When the coefficient is 1, it's the original, of course. When the coefficient is negative, is reflection. And when the coefficient is less than 1, is compressing. Suppose this interval now. Okay, this is compressing. Now it's stretching when it's greater than 1. Good? In conclusion, when you multiply a function by a constant, occur several effects. For example, if the constant is greater than 1, occur the stretch, vertical stretch. If the constant is a fraction, it's in between 0 and 1, occur the vertical compress. And if the constant is equal to negative 1, it's a reflection about the x-axis. Okay, the last transformation is when you multiply by the factor but inside the parenthesis. Okay, the analysis is a little bit different. Suppose we have a point in the original graph, is transformed, and another point in the new graph. As always, y1 is equal f evaluate at next one, and y2 is equal f evaluate in k x2. In this case, the supposition is that the y is the same. I suppose that y1 is equal to y2. So in this case, the argument in the same x1 is equal to k x2. Now, so for x2, x2 is equal to x1 divided by k, division. Now, the relationship between the coordinate original 1 and 2 are x2 is x1 divided by k, comma, and y2 is y1. Okay, let's see this effect graphically. This is x-axis, this is y-axis. We suppose here the original function. And we have here arbitrary point x1, y1. See, if k is a number bigger than 1, when you divide this, it's obvious that the coordinate x is decreasing. The effect is like that. This is the new x2. Now, it's obvious in this situation happen the horizontal compress. Horizontal compress is the effect. Likewise, see, k is a number fraction between 0 and 1. Now, when you divide by number less than 1, this is like increasing. So in this case, the motion is in this direction. This is the new x2. So this is horizontal stretch. Likewise, happen when the k is negative 1. And when the k is negative 1, it's something like that. If suppose you have the original and you multiply by negative 1, inside the parenthesis, suppose this is f of x, and when you multiply by negative 1, occur this effect is a reflection also, but reflection about y-axis. Right? Okay. In this case we have a horizontal stretch, compress, and reflection. Suppose I multiply, for example, this is our original graph, multiplied by a number greater than 1. Look at the effect. It's typical compression, horizontal compress. However, if you multiply by a number less than 1, suppose this 0.6, 0.3 is a stretch, horizontal stretch. Okay, now what happens when there's negative? Specifically negative 1 here. Is reflection about the x-axis. Look at the animation. Compress, in this case, because the coefficient is greater than 1. When the coefficient is less than 1, there's a stretch, horizontal stretch, and when the coefficient is negative, it's reflection. The specific at negative 1 is perfect reflection. In conclusion, when the coefficient you multiply by one coefficient inside the parenthesis of the argument of the function, and this factor is greater than 1, occur the compressing. However, when the coefficient is less than 1, it's in between 0 and 1 fraction, like a 1/2, 1/3, 2/3, whatever, it's a stretch, but horizontal stretch. And when the coefficient is specific at negative 1, it's reflection about the y-axis.